Hi everyone, my name is Silpa and my teammate Tanisha. We are from New Jersey Institute of Technology. Today we are going to give the cloud computing research paper presentation, and the topic is addressing the Straggler problem for iterative convergent parallel machine learning. Uh, Coming to the abstract, FlexRR is a solution designed to tackle the straggler program in iterative machine learning processes. Stragglers are computing nodes that lag behind others and slowing down the entire process. FlexRR provides two different key strategies to address this issue. First one is flexible synchronization model, and the second one is dynamic P2P reassignment. Flexible synchronization model means instead of relying on rigid synchronization points, FlexRR adapts its synchronization process dynamically. This flexibility helps mitigate the impact of stragglers by allowing the system to adjust its synchronization strategy based on the current state of computation. And the dynamic P2P reassignment means when stragglers are detected, FlexRR redistributes the work they were supposed to do other available computing nodes. This dynamic reassignment ensures that the overall workload remains balanced and preventing the stragglers from significantly delaying the computation. And here we can see the figure comparison of matrix factorization performance on EC2. This graph shows an average time per iteration for a collaborative filtering application while running 64 EC2 instances. And here we can see the motivation of iterative convergent machine learning algorithms. Here, the importance of iterative convergent machine learning algorithms are uh, matrix factorization for recommendation systems, for example, Netflix movie recommendations, and logistic regression examples are image text classification. And the last one, latent distillate allocation. This is for topic modeling, for example, discovering topics in document collections. These algorithms work by starting with an initial guess of the model parameters and then iteratively refining those parameters over multiple iterations to converge to the final model that best fits to the training data. And coming to the next slide, challenges with distributed implementations. Most of the bulk synchronization parallel model with input data parallelism. Here, BSP requires a synchronization barriers after each iteration, and SSP relaxes this by allowing a bounded slack, letting fast workers progress ahead to some extent, but doesn't fully address significant strategies. And these iterative ML algorithms use the BSP model and also SSP1. And coming to the next slide, here we can see the single thread machine learning process and parallel machine learning process. Here, for example, it's a web graph and it is a page ranks, and we can see the training data as input data and model parameters are the solution, and we can see the same thing in parallel machine learning process. Coming to the next slide, impact of stragglers and performance and convergence. Stragglers slow down distributed computing by making every iteration as slow as the slowest worker. And as the scale of computation increases, so does the impact of stragglers, leading to convergence times. And it means factors like resource contention, hardware issues, and load imbalances contribute to straggler occurrence and significantly degrading the performance. And the next slide, limitations of existing approaches for iterative convergent machine learning. Eliminating performance variation means existing techniques struggle to handle performance variations in distributed environments, and non-uniform resources such as those found in multi-tenant clouds are due to garbage collection. And speculative execution means while speculative execution can help mitigate straggler impact by running redundant tasks, and it is not suitable for machine learning algorithms with non-idempotent updates and limited its applicability. And the work stealing means work stealing approaches reactively redistribute tasks and but may not fully leverage machine learning algorithm properties and can incur significant data movement overhead. The last one, flexibility consistency. A flexibility consistency, it is useful for addressing small transient stragglers. Flexible consistency models like SSP may not efficiently handle prolonged straggler behavior commonly seen in iterative convergent machine learning scenarios. And the next slide, need for a new solution, FlexRR. Existing methods for handling iterative machine learning have some problems, so we need a solution for that. FlexRR is that solution. It uses a mix of flexible consistency and temporarily assigning work to fix the straggler problem in parallel machine learning algorithm. It's made specifically to work well with machine learning algorithms, helping them run better and faster, especially when they are doing lots of repetitive tasks. And design and main idea is that the overview of FlexRR's approach. Here, FlexRR tackles the straggler problem in iterative machine learning by blending two approaches. The first one is FlexRR consistency bounds, and the second one, temporary work reassignment. FlexRR consistency bounds, they employs the stale synchronized parallel model, which allows for flexible consistency bounds, and it means it can manage the trade-off between consistency and the performance more dynamically. And the temporary work reassignment means it also incorporates temporary peer-to-peer work reassignment. This feature redistributes work from slower workers to faster one, and it allowing uh, quicker progress while balancing the load across the system. And the next one, flexible consistency bounds. Flexible consistency bounds as implemented in the stale synchronous parallel model, and it extends the traditional bulk synchronous parallel approach. I mean SSP and the other one BSP. It permits workers to progress ahead of the slowest worker by a predefined slack period. This bounded staleness ensures that despite the asynchronous nature of the computation, convergence guarantees remain intact. And convergence guarantees are like by reducing the frequency of synchronization point, and SSP diminishes the synchronization overhead and thereby improving the overall efficiency in distributed computing environments. And the next one, rapid reassignment overview. Rapid reassignment is a method designed for efficient temporary redistribution of work. It's tailored specifically for iterative machine learning parameter servers. Unlike the basic approaches, like it optimizes work scheduling and effectively reallocating the task without unnecessary overhead. And it ensures that computational resources are utilized efficiently and maximizing performance without unnecessary computational burdens. The next one, rapid reassignment. Here we can see the image. This image presents a visual representation of the different stages or levels of progress in completing assignments or tasks. It issues three vertical columns labeled OK, fast, and the last one is slow. The OK column represents a person who is not in the need of assistance indicated by the label ignore, and the fast column represents a person who is making good progress indicated by the label I'm this far. And the last one, slow column, it represents a person who is behind or struggling indicated by the label I'm behind. This column only shows that they have started working on assignment 1. And the next slide, worker groups, and the other one, worker communication. In rapid reassignment, workers are organized into pre-assigned helper and helpee groups. Helper groups consist of a worker uh, capable of assisting others by taking on their tasks, while helpee groups comprise groups that can receive assistance, and this design with predefined groups ensures scalability by avoiding the need for all-to-all communication, and which can become inefficient as the number of worker increases. And additionally, workers periodically exchange the progress reports directly with each other, and enabling them to track their progress relative to their helper and helpee groups. This decentralized communication allows workers to identify themselves as either fast or slow based on their progress compared to others, facilitating the efficient task redistribution without centralizing coordination. And the next one, identifying stragglers. If worker falls behind a helper by greater than 20%, I mean, stragglers initiate the reassignment process by redistributing a smaller portion, I mean, typically uh, greater than 20% or set to 20%. When a worker identifies itself as a straggler for a particular iteration, it sends a do this message to request work reassignment to a faster helper. And the initial work reassignment, stragglers initiate the reassignment process by redistributing a smaller portion, it typically 2.5% of their workload to a faster helper. This reassignment is carefully managed by the minimize disruption and typically starting from the end of the task queue. And additionally, the helper preloads the input data required for the reassignment task to ensure the efficient execution. And here we have found a few problems in this research paper. The problem addressed in this paper is the straggler problem for iterative convergent parallel machine learning algorithms. Stragglers refers to the worker threads or machines that experience transient slowdowns are causing all other workers to wait for the slowest one at iteration barriers. And this is an important problem as a parallel or distributed machine learning is become increasingly common, and stragglers can significantly degrade performance, especially as parallelism increases. And the others convincingly motivate this problem by discussing the prevalence of transient slowdowns from various sources like resource contention and the garbage collection, etc., especially in multi-tenant cloud environments. These experiments also demonstrate significant straggler effects and the importance of both theoretical and practical ones. And these are some solutions also discussed in speculative execution is not applicable as ML updates shared state in a non-idempotent way, and the work stealing or shedding uh, solutions don't leverage machine learning properties or address transient stragglers effectively. And the last one, using flexible consistency models like SSP can help to some extent, but it is not sufficient for larger straggler effects. This related work session, the paper completely covers many existing techniques and highlights their shortcomings for this specific problem. The novel solution is like FlexRR, and which combines the two flexible consistency bounds, and it allows to faster workers to proceed somewhat ahead of slower ones. Second one is specialized temporary work reassignment mechanism, I mean, rapid reassignment to detect stragglers and offload work to faster workers. And this is a significant and original contribution tailored specifically for iterative machine learning training. And they evaluate using three real machine learning applications like matrix factorization, the second one, logistic regression, and the third one, LDA, on four cloud different platforms as well as a larger cluster. And this includes experiments with naturally occurring stragglers as well as a range of injected transient straggler patterns drawn from the previous work. The results shows that the FlexRR is highly effective and it consistently providing near ideal performance even under extreme straggler scenarios, significantly uh, outperforming BSP and SSP alone. And this paper is reasonably well organized and presented through the writing could be tighter in some sections, but we learned that the straggler problem is a significant issue for parallel iterative machine learning, and the FlexRR solution providing flexible consistency and bounds it combined with temporary work reassignment is an effective way to mitigate straggler effect for these algorithms. The next will be continued by Tanisha. Thank you.
Hello everyone, I'm Tanisha Bargujar and I will be continuing the presentation from here. So we'll be talking about the follow-up work reassignments. When an initial task is assigned to a helper, a small follow-up task like around 5% of the total work is assigned to the original person, which is the straggler who assigned the work. Now, as more helpers are assigned to the original task, even smaller follow-up tasks are created for the straggler. The remaining work is then reassigned in order from the end of the original iteration. Canceling reassignments. Once the straggler has finished the remaining work on the original task, they can cancel any unassigned reassignment. Before canceling a reassignment, the straggler must confirm with the helper that any updates made with the machine learning model have been acknowledged. This is to avoid accidentally canceling work that has already been done. This process helps to ensure that non-idempotent updates that cannot be repeated without causing unintended consequences, are not duplicated incorrectly. Now I'll talk about the advantages of rapid reassignment. Early straggler detection using well-defined iteration progress, in which like this refers to a system for monitoring how much of a task has been completed. By following a set of procedure for breaking down tasks into iterations, the system can identify tasks that are falling behind schedule early on. This allows for early intervention and reassignment of work to the helpers. Decentralized P2P design avoids bottlenecks. Now, this refers to a way of structuring a system where there is no single point of failure. In a peer to peer design, tasks can be distributed and redistributed among multiple devices or users without relying on a central server. This can help to improve efficiency and avoid delays that might occur in a central server more overloaded. Helper groups limit data movement overhead. Data movement overhead refers to the extra time and resources it takes to transfer data between devices or users in a network. By using a helper group, this workflow may limit the amount of data that needs to be moved around between team members. Input data preloading and update reordering for efficiency. Now, this refers to the technique for optimizing the way data is loaded and processed. Preloading data means anticipating what data will be needed and loading it in advance. Reordering updates refers to streamlining the order in which data is processed to avoid conflicts. Now we'll talk about the example scenario in detail. So, work group assignments, this refers to the initial allocation of tasks to team of the workers. Then we'll talk about the progress tracking. This refers to a monitoring how much of each task has been completed. Then we have straggler detection. This refers to identifying workers who are falling behind schedule with their assigned task. Then we have initial small work reassignment. When a worker is identified as lagging behind a straggler, a small portion of their work, which is like almost around 5%, is reassigned to a helper to get things back on track. Now we'll talk about helper preloading input data. To improve efficiency, helpers can anticipate the data they'll need to complete their reassigned task and load it in advance. follow up larger reassignments. If the initial reassignment is not enough to get the task back on schedule, even larger portions of the work can be reassigned to the helpers. Completing reassigned work. If the original worker, the straggler, catches up and finishes the original task, they can cancel any reassignment that haven't yet been completed by the helpers. Updating the ML model state. The workflow mentions here that the system updates an ML model likely to inform future reassignment decisions. It's important that these updates are done correctly to avoid introducing errors into the system. Implementation in the FlexRR architecture. We have distributed processing here, where FlexRR uses a distributed processing architecture where one FlexRR process runs on each node in a cluster. This means that the workload can be divided and processed in parallel on multiple machines. Then we have worker threads. These worker threads are responsible for executing the ML computations. The number of worker threads is typically equal to the number of cores in the machine. We have background threads then. FlexRR process also have background threads that handle internal FlexRR functionality. This might include tasks such as communication with other FlexRR process or managing the parameter server. The parameter server we are talking about is the FlexRR uses a parameter server to store the current state of the ML model. This allows all the worker threads to access the same model parameters. Now we have shared parameter server. The parameter server is shared, which means that it is divided up into multiple pieces. This can help to improve the performance by allowing multiple worker threads to access the parameter server concurrently. Last we have is read-write interface. So in FlexRR, it provides a read-write interface for model parameters. This allows ML applications to update the model parameters as it's needed. In this diagram, we can see that we have worker, we have data, and then this is a parameter server. So worker as in the W, these are the processing units that carry out the machine learning task. The diagram shows that the multiple workers are there, which indicates that FlexRR can be run in a distributed fashion across the multiple machines. Now the data represented by D. This represents the data that the workers will process to train the machine learning model. And the parameter server here, this is the central repository that stores the current state of the machine learning model parameter. Workers can access and update the model parameters from the parameter server itself. Now we'll talk about the parameter server integration. So the leverages efficient client-side caching on worker machines to reduce the data transfer. Then we have the support from both the BSP and SSP training models for its flexibility. And it maintains data freshness with a staleness bound for the cache values. And we have integrated seamlessly with our fault tolerance and checkpointing mechanisms from the lazy table system. Then we have the rapid reassignment, handles the work migration for efficiency. Now we'll talk about the evaluation of the experimental setup. Here, platforms and clusters. The experiment will be run on a different cloud platforms that can be Amazon EC2 and any local cluster to see if the effectiveness of the straggler mitigation techniques vary across these environments. In the application benchmarks, three different machine learning algorithms will be used as benchmarks: matrix factorization, the MF, or the multinomial logistic regression, and the LDA. These algorithms are chosen because they represent different workload characteristics that may be affected by stragglers differently. The straggler patterns evaluated here is that the system will be evaluated under four different straggler patterns. First is naturally. Naturally occurring on public roads. This refers to running on experiments on public cloud platforms where stragglers might occur due to factors outside the control of the experiment, such as variations in network performance or resource availability on the cloud provider's infrastructure. Then we have the injected ones. Slow worker distributed machines, power law. These are likely simulated straggler that will be artificially introduced into the experiment to assess how well the system handles different types of straggler scenarios. We have one slow worker. This might simulate a worker that has consistently lower processing power than the other workers. Then we have disrupted machines. This might simulate a worker that is temporarily unavailable due to a network issue or hardware malfunction. The last we have is the power law. This is likely it refers to a scenario where stragglers occur according to a power law distribution, which is a statistical distribution where the probability of an event happening is inversely proportional to its size. So, there is a higher probability of few very slow workers than many moderately slow workers. Then last we have is metrics. This experiment will measure two main metrics, time per iteration and time to convergence. Time per iteration refers to the amount of time it takes to complete each iteration of the machine learning training process. And time of convergence refers to the total amount of time it takes for the machine learning model to reach the desired level of accuracy. Okay, so here we can see the comparison between two bar charts showing BSP, SSP, BSP-RR, and Flex-RR, and their performance is on the different platforms, which shows that delay per iterations we can see. Now we'll talk about the main results. So public cloud platform, it focuses on improvements on Amazon EC2 and Amazon Azure, which are both cloud computing platforms that offer virtual machines that can be used for running distributed machine learning workloads. We have speed test and convergence test. These tests are likely designed to measure how quickly the machine learning models can be trained using different execution modes. Convergence refers to the point where the training process reaches to a desired level of accuracy. We have straggler patterns. Straggler refers to the machines or core that fall behind in their reassigned task and slow down the overall training process. And we have FlexRR performance improvement. FlexRR can significantly outperform BSP and SSP in terms of training speed, especially when stragglers are present. For example, FlexRR can be up to 56% faster than BSP on Microsoft Azure with no synthetic delays introduced. Now we'll talk about the injected patterns here. Slow worker pattern. This pattern stimulates a worker that has consistently lower processing power than the other workers. This could be due to the hardware limitations or the software issues. FlexRR mitigates the impact of slow workers. So FlexRR can improve the overall training speed even when there are slow workers present. This is likely because FlexRR can identify slow workers and reassign these tasks to other workers that are available at that time. We have 10x faster than BSP SSP at 400% delays. So this means that FlexRR was able to train the machine learning model 10 times faster than BSP and SSP when there was a simulated delay of 400% on the tasks assigned to some of the workers. Now we have the convergence test. These tests are likely to be designed to measure how quickly the machine learning models can be trained using different execution modes. Convergence refers to the point where the training process reaches a desired level of accuracy. And we have FlexRR maintains near ideal convergence. So FlexRR can achieve the ideal convergence almost as quickly as the ideal case, even when there are slow workers present. Okay, so as you can see, the graph shows the results of the evaluation we did. Even when the delay occurs, the FlexRR is consistent and doesn't show a really huge difference as we can see in the graph, and it maintains its performance. Now we have the other evaluation results. Evaluation on uneven workload distributions. This refers to a scenario where some machines are assigned more work or take longer to complete their assigned task compared to the others. This can slow down the entire machine learning training process. So, FlexRR mitigates uneven workloads. So, FlexRR here can improve the training speed even when there are uneven workloads due to the stragglers. And we have experiments with the partial application of input data. So, this is likely to refer to a technique where only a subset of the data required by a worker is copied to the worker machine. This can help to reduce the amount of data transfer required, especially when the workers are geographically distributed in a cloud environment. Now we have the sensitivity analysis of FlexRR. This refers to the process of studying how FlexRR performance is affected by the different settings. This configuration parameters might include things like the number of helper workers assigned or the size of the data chunks transferred between these workers. Here we can see the charts showing the helper group size, the work assignment size, the message check frequency, and we can see that the fluctuations in the FlexRR is much less compared to the others. So in conclusion, FlexRR is a system designed to improve the performance of a machine learning workload. It is effective at mitigating the impact of stragglers. The stragglers here are workers in a parallel computing system that take much longer than others to complete their assigned task. FlexRR achieves this by using flexible consistency bounds and temporary peer-to-peer work reassignment. The research paper also mentions that experiments on real machine learning applications showed that FlexRR achieved significant performance improvement over the existing methods. We would like to end our presentation here. Thank you.